Okay, these are going to be some notes on the derivatives of hyperbolic functions. You should have already seen a video that describes the origin of hyperbolic functions, how they originate from the unit hyperbola as opposed to the unit circle, which is where trig functions originate from, and just gives you a basic overview so that when you see something like the hyperbolic sine of x equals e to the x minus e to the negative x divided by 2. This should not be the first time you're seeing that, so if it is, please watch the other videos. The definition for the hyperbolic cosine of x is going to be e to the x plus e to the negative x. Once you have those two definitions, you're going to see a lot of similarities between the relationships of hyperbolic functions to each other and the relationships of trigonometric functions to each other. For example, the hyperbolic tangent of x is the hyperbolic sine of x divided by the hyperbolic cosine of x. That's very similar to trig functions. The hyperbolic cosecant of x is the reciprocal. It's 1 divided by the hyperbolic sine of x. Just like the hyperbolic secant is going to be the reciprocal of the hyperbolic cosine. And the hyperbolic cotangent of x is the reciprocal of the hyperbolic tangent of x. So at first glance, these seem very, very related to trig functions, and in some ways they are, but in some ways they definitely are not. For example, this is the graph of f of x equals the hyperbolic sine of x. Notice it has some things in common with sine x and some things that are not in common. So for example, this is not a periodic function, right? It doesn't continue in a pattern over certain periods. It is, however, an odd function, so that it has in common with sine x. Visually, it actually looks more like a cubic function, which again, it's not, but this is what the graph of hyperbolic sine looks like. The domain of this function is going to be negative infinity to infinity, and the range of this function goes negative infinity to infinity as well. It is odd, meaning that it has symmetry with respect to the origin, as opposed to the hyperbolic cosine of x. Notice this one, the domain is also negative infinity to infinity. However, the range goes from 1 to infinity. Visually, this looks more like a parabola than it does cosine x, that's for sure. This is not a parabola. It is similar in appearance, but it does not have the same properties. This is actually what's referred to as a catenary. And if you were to do a point-by-point plotting of e to the x plus e to the negative x and divide it by 2, this is the graph that you would come up with. Of all the hyperbolic functions, the hyperbolic cosine, because of the fact that it has the shape of a catenary, is probably the most used of the 6. It has some really prevalent physical applications. Take a look.
You may be aware that mathematics is all around us. It's in the petals of a flower, it's in the honeycomb of a beehive, it's in the spirals of a seashell. So it's all around us in the natural world, but what about closer to home? Here I have a piece of rope. If I hold it between my hands, it forms a curve. This is called a catenary curve, and it is not a parabola. It is its own type of curve with its own type of mathematical description. The word catenary is derived from the Latin for chain because it's the shape formed from any chain or rope hanging freely under its own weight. And you'll see this simple and beautiful piece of mathematics everywhere, from the wires in an overhead power line to the strands of a spider's web. But why do we see this curve appearing again and again in the natural world? To answer that question, we're going to turn to the world of bubbles. To minimise their surface tension, bubbles form perfect spheres. If we try to form a bubble between two rings, it cannot make a sphere, so instead makes a curved shape. This time, to minimise its surface tension, it makes the catenary. So a chain, like in the world of bubbles, wants to minimise its tension, so forms the catenary, and it is not a parabola. The parabola is the arc of a ball flying through the air. Its mathematical description is y equals ax squared plus bx plus c. By eye alone, it looks like a catenary. Galileo realised that the curve of a free hanging chain was very similar to a parabola, but something was amiss. The mathematical description of a catenary is actually quite different. It is y equals a cosh x over a. That's equal to a over 2 outside of e to the power x over a plus e to the power minus x over a. The curve changes as the distance between the two ends and the length of the chain changes, but they can be described with the same formula and are never parabolas. Man uses this natural form in the worlds of engineering and architecture. For example, the wires of a suspension bridge are parabolic due to the weight of the bridge it carries. But without this weight, it is more like a simple rope bridge carrying the same weight along its length and will again be a catenary curve. But if the catenary is the shape of a rope or a chain that minimises forces in tension, then by turning this upside down, we form an arch which minimises the forces in compression. And it's actually the strongest kind of arch, strong enough to support its own weight. For example, that's what the master builders of the Middle Ages did to construct this, the ceiling of King's College Chapel in Cambridge. So to make the strongest kind of arch, you can simply mark out the shape of a free hanging chain and turn that shape upside down. So now that you know what a catenary curve is, you'll be able to spot it everywhere. So next time you see an archway, a bridge, or a spider's web, remember, you're seeing mathematics.
Okay, so now that we know some of the physical applications, let's talk about some of the identities. And again, these should be a little familiar because they very much resemble the trigonometric identities, but they are not the same. The hyperbolic sign of the opposite of x equals the opposite of the hyperbolic sign of x. That is because of the fact that hyperbolic sign is an odd function. Just like this property holds because hyperbolic cosine is even. When you input the opposite of x, you get the same thing as when you input the original x. Now this one's where we're really going to start to see a difference. See, in trig functions, it's sine squared x plus cosine squared x equals 1. That's not true in hyperbolic identities. In hyperbolic identities, it's hyperbolic cosine squared x minus hyperbolic sine squared x equals 1. That's because these are based on a hyperbola instead of a circle. Similarly, we've got 1 minus hyperbolic tangent squared x equals hyperbolic secant squared x. That's not the same sign, SIGN, as the trig identities. We also want to talk about the derivatives of hyperbolic functions. Not surprisingly, the derivative of hyperbolic sine x is going to be hyperbolic cosine x. But surprisingly, the derivative of hyperbolic cosine x is hyperbolic sine x. There's no sign, SIGN, difference. They're both positives. The derivative of hyperbolic tangent x is hyperbolic secant squared x. The derivative of hyperbolic cosecant x is negative hyperbolic cosecant x hyperbolic cotangent x. But the derivative with respect to x of hyperbolic secant x is negative hyperbolic secant x hyperbolic tangent x. And the derivative of hyperbolic cotangent x is negative hyperbolic cosecant squared x. So again, they're similar, but all three on the left are positive and all three on the right are negative. So there's some sign differences here. So when we go to look at some examples and talk about derivatives, once we have those basic 6 hyperbolic derivatives, we can go ahead and just apply all our other differentiation rules. So when we want to talk about the derivative of hyperbolic cosine of the square root of x, notice it's not just hyperbolic cosine of x, there's a function inside here, which means we're about to use chain rule. so that the derivative with respect to x is, we need the derivative of the outside function, which is hyperbolic sine. Don't touch the inside function, and then you multiply that times the derivative of the inside function, which is 1/2 x to the negative 1/2. And yes, of course, there's other ways to write this, but that's the basics of this derivative. If we wanted the derivative of f of x equals hyperbolic secant x times 1 plus the natural log of hyperbolic secant of x, notice these two are not being multiplied. If these were being multiplied, this would say ln x hyperbolic secant x. You'd have an x here. This is multiplication. This is not. Be very careful on the difference. You have a couple ways you can correctly approach this. You can either leave this as is and use product rule with hyperbolic secant acting as your first function and 1 plus the natural log of hyperbolic secant x acting as your second function. That would be a correct way to go about it. Or you can distribute the hyperbolic secant x to both terms. Now notice when you do that, you're going to end up with a product rule anyway from your second distribution. So I'm going to go ahead and just leave this as is and go straight to product rule. But if you wanted to do it the other way, that would be correct as well. So the derivative with respect to x, I'm going to take the derivative of hyperbolic secant of x first. And as we just discussed, that is negative hyperbolic secant x hyperbolic tangent x. I'm going to leave the second function as is, 1 plus the natural log of the hyperbolic secant of x. I'm then going to add to that, I'm going to drop down a line so I have enough room, this one's going to be long. I'm going to leave the hyperbolic secant of x alone, and then I'm going to take the derivative of 1 plus the natural log of hyperbolic secant of x. The derivative of 1 is easy, that's just 0. The derivative of the natural log of the hyperbolic secant of x, this is going to require a chain rule. The derivative of the outside function, that's the derivative of the natural log first, so I need 1 over, don't touch the inside function, hyperbolic secant of x, times the derivative of the inside function, so that's times the derivative of hyperbolic secant of x, which we just said is negative hyperbolic secant x, hyperbolic tangent x. Okay, I'm going to clean that up a little bit so that I have negative hyperbolic secant x, hyperbolic tangent x times 1 plus the natural log of hyperbolic secant of x. And then the negative, I'll go ahead and change this to a minus. And notice here that this hyperbolic secant x will cancel this hyperbolic secant x, or you can think of these two as canceling. It doesn't matter. Either way you go, what you're left with is hyperbolic secant x, hyperbolic tangent x. Now you could rewrite this a couple other ways. You can factor out the hyperbolic secant x, hyperbolic tangent x. You can factor out negatives, but the basics of this derivative are correct as is. And that's how you take derivatives of hyperbolic functions.